In this video, we are going to talk about square roots and real numbers. In the last video, we talked about powers and exponents, so square roots is basically going to be the opposite of that. And then we'll give you some definitions for real numbers and other types of numbers that make up our curriculum. So with that said, let's dive into square roots. This symbol in front of you is called a radical, and it denotes that we should use a square root. Now, a square root is when we want to take a perfect square such as, let's say, 25, and we're trying to find the number or numbers that when squared or multiplied by itself will give us 25. Now, 25 is a perfect square because it has a whole number as its square root, which is plus or minus 5. Generally, square roots have two answers, a positive version and a negative version. And here's why. If I have 5 times 5, that's going to give me 25. If I have negative 5 times negative 5, a negative times a negative is a positive, so I will also have a positive 25. So whenever we take a square root of something, we get a positive and a negative version of the answer. And the numbers we hope to take square roots of are our perfect squares. Perfect squares such as 1, 4, 9, 16, 25, 36, 49, and hopefully you get the picture. These all, and plus many, many more, when you take the square root of them, will give you a whole number. Square root of 1 is just 1, plus or minus. Square root of 4 is plus or minus 2. Square root of 9 is plus or minus 3, and so forth and so on. But what if we have a number that isn't a perfect square? Well, we can still take a square root of it. We might want to use our calculator, but we can also guesstimate what it would be based on how close it is to a perfect square. So let's take a look at another number. Here we have the square root of 19. 19 is not a perfect square because 19 is actually prime. 19's only factors are 1 and 19. But we can come up with an approximation of what its square root is because we know 4 times 4 is 16, and 5 times 5 is 25. So the square root of 19 has to be between 4 and 5 because the perfect square of 4 is 16, the perfect square of 5 is 25, and 19 is between 16 and 25. Now we can say that 19 is closer to 16, so the square root of 19 is probably going to be closer to 4 than it is to 5. If we want to get even closer to what the actual square root is, well then we're going to have to do some guessing and checking. We're going to have to say, well, what is 4.2 squared? And if I were to work that out, we would get 17.64, which is close, but we probably want to see if we can get closer. So then we might want to try 4.4 squared. And if we take 4.4 squared, we get 19.36, which is now a little bit too high. But we are definitely closer than we were with 4.2. And depending on how close you want to get, we could then say, well, what if it was 4.35 squared? And we could keep adding decimals to try and get closer and closer and closer until we get the exact number. I don't recommend doing that. It's not a valuable use of your time. But we can at least say, hey, the square root of 19 is approximately 4.4. Let's try one more. This time we have the square root of 32. Square root of 32 is going to be somewhere between 5 and 6. We know this because 5 squared is 25, 6 squared is 36, and the number under the radical here is between 25 and 36. My guess is that it's going to be closer to 6 than it is to 5. But just like before, we're going to want to get an approximate value by guessing and checking. So let's jump right into the middle between 5 and 6 and see what is 5.5 squared. And if we multiply it out, we get 30.25, which, like before, is kind of close, but we can see if we can get a little bit closer. So let's try 5.6 squared. And this time we get 31.36, which is even closer, but maybe we can try one more and see what we get. So we can try 5.7 squared. And that's going to give us 32.49. Now we have to ask ourselves, between 5.6 and 5.7, which one is the better estimate? Well, 31.36 is 0.64 away from 32, where 32.49 is only 0.49. So technically 5.7 is just a little bit closer. And in reality, it's actually still somewhere between these two numbers. So that's how we can find an approximation of our square root when we are dealing with a number that is not a perfect square. Now, let's talk about real numbers. Now, the fancy definition for real numbers is all numbers that can be represented on a number line. This includes numbers like, -7, 0, 5.2, and the like. But under the umbrella of real numbers, we have several subcategories that numbers could fall into. So we're going to address these subcategories, give some examples of them, and see what we can learn from it. And this all is going to start with natural numbers. So in this circle, I'm going to use for natural numbers. Natural numbers are numbers such as 1, 2, 3, and so forth. They are also denoted by the letter N. The ones they use in your book are a little fancier than the N that I drew, but this is going to be the best that I can do. Now, natural numbers make up a lot of the numbers that we've used, but this is the most specialized category that we're dealing with. The next level up, which includes all natural numbers, but has an extra addition, is the category of whole numbers, which is denoted by W. And the addition that whole numbers includes is all of our natural numbers plus 0. So if we are talking about whole numbers, we are saying anything that is greater than or equal to 0. If we are talking about just natural numbers, we are talking about anything that is greater than 0, not inclusive. Now the next category up that envelops all of these as well, but adds more to it, is our integers, which is denoted with the letter Z. I don't know why they used Z, but they did. Integers include, just like you can see with this diagram that I'm making, It includes natural numbers. It includes whole numbers. But now we're also using our negatives. So things like -1, -5, -7. Integers includes pretty much everything from negative infinity all the way up to positive infinity. And then the last category that's going to continue to use all of these but add more to it is what are called rational numbers. So this encompasses all of our whole number, natural numbers, and integers, but now we have rational numbers as well, which is denoted by the letter Q. Once again, no clue as to why they use the letter Q, Z, or, well, the others make sense. Whole numbers start with a W and natural starts with an N, but for Q and Z, that's kind of weird. Now, rational numbers are anything that can be expressed as a fraction and where the top and the bottom are both integers, as long as the bottom is not 0. So we have rational numbers such as 3/5 or -6/8. These are considered rational numbers. Now, with our rational numbers, we have two special subcategories that I can't use this picture for because we're not going to be dealing with everything in here. We're just going to be dealing with some decimals. So, let me slide this out of the way. And we have what are called terminating decimals and repeating decimals. These are part of our rational numbers, but they have special properties. A terminating decimal is something that, after a certain point, the decimal ends, like 1.5 or 2.85. The decimal, when it's worked out, doesn't go past here, and if it does, it's only zeros. Same thing here. I could have numbers after this 5, but the only thing that works to make them terminating decimals would be 0. Repeating decimals, on the other hand, never end, but there's a pattern. It could just be something as 3.333, and it's just going to keep giving us 0.333 forever. So we would say that instead of writing all of the 3's out, we have a bar that goes above it, and that would be 3.3 repeating. Or we could have other numbers, such as 2.141414, that have more than one number repeating, but still the pattern repeats. So just like before, I wouldn't write out all of those 1/4s, but instead put the repeating bar above both of them to show they both repeat at the same time. So we've got a lot of things going on here. We've got all these types of numbers: natural numbers, whole numbers, integers, rational numbers. And with rational numbers, we also get terminating decimals and repeating decimals. And then lastly, our final little subcategory in real numbers that is not part of all of this. It's in its own special area. And these are called the irrational numbers. Now, irrational numbers are numbers that cannot be expressed as a fraction, and typically they are things such as the square root of a whole number that is not a perfect square. So there's our square root of 19 again. That would be considered irrational. it's going to give us a decimal that continues forever and there's no pattern to it. So it's not like our 0.141414 where it just keeps on going in the same order. It changes, it's random, and it never stops. Now, it could also be one of the more famous numbers, which is the number pi. Pi is also considered an irrational number because you cannot give it an exact form as a fraction, and pi never ends. It's 3.1515926, and then it just keeps on going forever and ever. So these are called our irrational numbers. If you see a square root symbol and it is not a perfect square underneath, you're going to have an irrational number. Same thing if you see the pi symbol. So that's it for this video. We've talked about square roots, and then we've talked at length about all the different types of real numbers. Once more, just to reiterate, we have natural numbers, which is all of our positive whole numbers, not including 0. Then we have whole numbers, which is everything that is greater than or equal to 0. We have our integers, which adds negative numbers to the mix. We have our rational numbers, which adds in all of our fractions and decimals, which could be terminating decimals or repeating decimals. And then lastly, for real numbers, we have irrational numbers involving square roots and pi. I hope this video was useful, and good luck.